Hello everyone, welcome to the second lecture of ninth week of Scalable Data Mining course. In this lecture, we are going to start the new subject, which is also the last topic of this course, which is large scale machine learning. Okay. Okay. So basically, as you can understand, much of machine learning is optimization. Okay, so we have just given some representative formulations, which is by no means exhaustive set of formulations. Okay, so you have for example this optimization problem, which is uh, for those of you who can recognize this is a support vector. Most of you know this is the support vector machine formulation. Okay, uh, so this is a formulation for linear classification. Okay, and your after you do all the maths or all the modeling and everything, your job is finally to estimate this set of parameters w, okay, by minimizing this objective function, okay, subject to this set of constraints. Okay, this is the support vector machine formulation. Okay, uh, here the thing to note is that n is the number of data points. Okay, and so basically these sums are over the number of data points, and these constraints are also number of data points, and there is a simpler way of writing this also. uh, yeah, okay, then there are the maximum likelihood for estimation of models. So here you have a probabilistic model p theta, which is a function of parameters theta, okay, and data points xi. So here it could be xi and yi both. Okay, and again there is a sum over the number of data points. Okay, and you have to find theta which maximizes this log likelihood function. So this is called the log likelihood function. This is the probability of the data. Okay, uh, here again the crux of the learning algorithm is solving this particular optimization problem. So the maximum the time that the computer spends, okay, in learning is, so most of that time is actually in solving this optimization problem. Okay, so these two are supervised learning. Okay, and there are many. So notably there is the um, uh, okay, so this is supervised learning. So there are many such you know many such formulations for supervised learning. So notably there is the deep learning formulation, and so on and so forth. Okay, there are also unsupervised learning problems. So this is the k-means clustering problem, where your task is to estimate the cluster centers which minimize this objective function. Okay, or there are recommendation problems where the task is to estimate certain latent representations of topics. Okay, here also the problem is that of uh, that of uh, basically minimizing with respect to these parameters, which are these centers of clusters, this particular objective function. And again you see this sum is over all data points. So this inner sum is over all data points of cluster I, and outer sum is over all clusters. Okay, so basically this sum is over uh, uh, all data points. Okay, so this is a recurring theme in machine learning, where, so what is the recurring theme? The recurring theme is let us say, let me put it here, um, the recurring theme. So the recurring theme is that you have a certain function, okay? Without loss of generality, we can call this the loss function, okay? Of data points, okay? Data points could, so again, without loss of generality, we could stick to supervised learning, but it doesn't really matter. Many of these things also go into unsupervised learning settings, or even semi-supervised learning settings, okay? Okay, so there is this loss which is a function of the data points, okay, and some parameters. So let me put here and some parameters theta, okay, and this loss is kind of summed over all data points, okay, and this is the total loss, okay, which is a function of theta, okay, and this is something that we want to minimize with respect to theta, okay. So now you see there is the next further step, which is that this summation, okay, so here without loss of generality I can also minimize 1 by n sum over loss. In fact, it is normally done. So your loss in deep learning settings, for example, is written as 1 by n summation over I is equal to 1 to n loss of loss of xi, yi and theta, okay. Now this um, is something that we compute in practice, but this is actually, so we can think of this as expectation over x, or let me call this just x and y. So here x and y are random variables, okay, and let's say these are drawn from some distribution p, okay. This is the distribution of real world examples, okay, and then loss of x comma y given theta, okay. So here what we are saying is that we are taking this as sort of an approximation for what we really want to minimize. What we really want to minimize is the expected loss of all data, okay, and then estimate the model parameters theta. But since this expected computation of this expectation will exactly will require infinite number of examples, so we take a data set of n examples, okay, and then we minimize this particular loss function, which is 1 by n summation over loss. So this is kind of a universally accepted point of view, but more formally this was mentioned in a paper by Leon Botiu, okay, uh, in 2008, okay, where he claimed that the machine learning is actually a stochastic optimization problem, okay. So what is a stochastic optimization problem? Stochastic optimization problem is an optimization problem where your actual objective function is actually a random variable. So what is the random variable? The loss is the random variable. Why is it a random variable? It's a random variable because it depends on these random variables x and y, which are data points and which are drawn from some probability distribution. Okay, and then now we want to, so obviously we cannot optimize a random quantity, okay, because it's already always changed, so or it has a distribution. So instead we optimize in stochastic optimization. Generally we optimize some deterministic property of a random quantity or a stochastic quantity. Okay, in this case the deterministic thing happens to be the expectation or the mean, okay, which is also the most natural thing to optimize. So instead of optimizing the random quantity, we optimize the expectation of that random quantity. Okay, and there are many different things. Stochastic optimization is a large branch of study in itself, and people try to optimize sometimes variance of a random quantity and many other things. Okay, but the simplest form of stochastic optimization, one can say, is to minimize or optimize the expectation of a random quantity. Okay, and with this formulation, okay, what Leon Bottou did is he sort of said that, machine learning is really a stochastic optimization problem. Okay, and okay, so this is one part of the story. Okay, now let us come to the other part of the story. Okay, so suppose we take the deterministic loss function. Okay, here L is the loss function. Okay, this L is the loss function. Now suppose we take the deterministic loss function. Okay, and then we want to optimize it. So how do we optimize? Okay, again a simple gradient descent or subgradient descent. So we will not go too much into technical details of what is a subgradient descent uh, and all, but basically what you can say is that gradient descent only works for objective functions which are differentiable. Okay, but subgradient descent also works for non-differentiable objective functions which are convex. Okay, so subgradient descent not only works for differentiable of objective functions, okay, it also works for non-differentiable objective functions, okay, which are convex. And how does this work? So this works basically in the following way, that if you have, let's say, this kind of an objective function which is convex but not differentiable here at this point. Okay, as you can see there are two gradients. So one is, if you approach from the left side, this is one gradient. Okay, and if you approach from the right side, this is the gradient. Okay, yeah. Okay, so what subgradient descent says is a subgradient direction is all the intermediate directions. So if this is one gradient direction, this is another gradient direction, all linear combinations. So basically, uh, uh, yeah. So basically, this, all these are subgradient directions. Okay, uh, and then so one can formally define this, but essentially all these are subgradient directions. And basically what subgradient descent algorithm does is it uh, uses the subgradient as the gradient at the point of non-differentiability. Okay, so or at the point of inflection. Okay, so sorry, at the point of non-differentiability, not point of inflection. Okay, so now, and the algorithm is something like this, that you you start with a random set of parameters. So here W is the parameter. Okay, and xi and yi are your loss functions. Okay, and then you just you calculate wk plus 1, given that you already know wk, okay, using this formula, which is the gradient step, which is that you take a step, so you deduct a step size, so eta t is step size, times this gradient of the objective function or subgradient of the objective function with respect to the parameter w. Okay, so here we are saying that because your whole objective function is actually a sum of many different loss functions, one at each data point, then your gradient is also sum over all the individual gradients. Okay, and this is how you update the w, and this is your simple subgradient descent algorithm or your batch subgradient descent algorithm. Okay, and you select eta t according to some step size rule, so that there is your sort of descent is guaranteed. Okay, that is your objective function value either remains the same or decreases with this wk. Okay, okay, now um, so you see the property of this algorithm is that your entire training set has to be examined or has to be processed for each update. Okay, now this is very slow when n is large. Okay, uh, which is also the case when you are, for example, it is very relevant in today's world when you are training very complex deep learning models. Typically your n can be in millions. Okay, uh, so basically each step computation here is going to take a substantial amount of time, like a few seconds or maybe a few minutes even on your computer. Okay, so this is the setting. Okay, so how can you uh, so how can you optimize this? Okay, so what Leon Batu suggested is that since your optimization problem is anyway a stochastic optimization problem, okay, you use stochastic subgradient descent instead of standard subgradient descent. Okay, so what does stochastic subgradient descent do? Okay, so stochastic subgradient descent, it does basically exactly the same thing, except that it uses the stochastic gradient. So it uses the stochastic gradient. Okay, so what is the stochastic gradient? So basically, suppose you have this loss function, remember the random loss function, okay, which is a function of x and y, and also it is a function of theta. Okay, now you can just differentiate this with respect to theta. Okay, and this is your stochastic gradient. So again, the stochastic gradient also is a random quantity. Okay, just like your original objective function was a random quantity, your stochastic gradient is also a random quantity. It depends on the random variables x and theta. Okay, so now hence your whole parameter update sequence is also a random quantity. Okay, so you basically update your loss with respect to a stochastic gradient. Okay, now since the stochastic gradient is a random quantity, your sequence of updated parameters is also a random quantity. Okay, so at the end of it, what you do is you get uh, you get the random you get a sequence of random w's, and then you know there are certain guarantees on this set of random w's. Okay, now these guarantees are uh, we will come to the guarantees. Okay, uh, but essentially you can think that this random sequence of w's is also somehow minimizing the expected loss. Okay, this is what is going on. Okay, now what happens in practice in our case or in the case of machine learning? So this is the general stochastic gradient descent. Okay, in case of machine learning, this is very appropriate because we know that our data points xi and yi are random sequences of data. Okay, so we know that our data points xi and yi are random samples of the data. Okay, so we can just construct the gradient by evaluating the gradient of the loss function at a given data point. Okay, now if this is the case, okay, um, then what does our algorithm become? So our algorithm becomes something like this, that you take the our algorithm becomes the following, that you take um, the your data set, okay, your training data set, okay, and then you choose examples from it randomly. Okay, so the most common thing that is done is you just do a random permutation of your training data points. Okay, and then you you just run your uh, gradient descent with the instead of the gradient or subgradient descent, where instead of the gradient or the subgradient you calculate the gradient of this or the subgradient at a particular data point. Okay, or at the data point in the order, okay, in the permuted order that you have chosen. Okay, and that's all. Okay, uh, and you generate a sequence of w. Okay, okay, now there are there are two advantages of this. Okay, one is that you every update to w, okay, earlier if your n is large was taking a lot of time. Okay, now it is just one data point, so it is like 1 millionth of the time. Okay, so it is like coming down to again from seconds or minutes to milliseconds or microseconds. Okay, that is number one. Okay, but the more important thing, or yeah, both are important, but so the important thing is that this has now become an online learning paradigm. So what does online learning mean? It means that you don't have to go through the entire data set to even do the learning. So it can also happen that you only cover part of the data set. Okay, or you so the main point here is that you are somehow getting one random example at a time. Okay, something like the streaming model, and you are doing the update at any point in time. You have a candidate model w. Okay, after each update you have a candidate model w. Okay, so suppose you have been only able to process, let's say, 70% or 90% of the data set. Okay, at that point in time also you have a model. Okay, it may not be the best model, but you have a model. Okay, Uh, and now, so the result that is most commonly used or most widely known also is that if your loss is convex, okay, then in the expectation sense, this is guaranteed to converge to a local minimum. Okay. Okay. So this is kind of like a sample plot of the of a run of a SGD algorithm. Okay. So on x-axis are the iterations or the updates, and on y-axis are the objective function values. Okay. Now, your yeah, so you can see there is a randomness. It is not a descent method, unlike gradient descent or batch gradient descent algorithm, where you basically uh, in every iteration your objective function value actually decreases, or you can at least ensure that your objective function value decreases. Okay, but here it is not like that. You can see that the objective function value keeps jumping around. Okay, and that is understandable because your gradients are very noisy gradients. Okay, so these are gradients using only one data point. Okay. Okay, so let us dive into the guarantees that we can give for stochastic gradient, or what kind of guarantees can we get for stochastic gradient descent if your loss function is a convex loss function. Okay, so your notation is going to be that you have a data set of size uh, m, okay, or rather capital N, let's say, okay, and you have this total loss function, okay, which is an average of loss over the entire data set. Okay, uh, and yeah, so if you have a linear model, okay, then your loss is basically something like this. Okay, where you have a feature transform of x, and then your model is basically theta transpose x, and your label is y, and you have the loss function. Okay, now your dataset D, as mentioned earlier, is drawn IID from some distribution P, and your problem is to minimize this. Okay, now your algorithm is for this analysis we will take a somewhat weird algorithm. So your update is exactly as we described, that for a fixed number of updates. So typically you run a stochastic gradient descent for a fixed number of updates. Okay, so you start with a random parameter, and for a fixed number of updates you run this update equation. Okay, so theta t plus 1 is equal to theta t minus eta t times gradient of the loss. Okay, and then you just return your optimal parameter as this weighted average or step size weighted average of this theta t. So remember, your theta t is actually a random quantity. So your theta bar is also a random quantity, but now you are doing some kind of averaging here. The averaging being that you are giving more weightage to those theta t's which were obtained when your eta t was the highest. Okay, now this is somewhat counterintuitive, because typically what is your step size schedule? Your step size schedule will typically be, your eta t will typically be decreasing. Either it will be a constant, in which case it is just an average, okay, or it will typically be decreasing. So you are giving more weightage to initial theta t's which are generated. Okay, but nonetheless, you are giving a lot of weightage to the theta t's which are generated later also, especially if you take this capital T to be very large. Okay, okay, So this is your objective. In either case, see if you can guarantee that this theta bar is close to the optimum in some sense, okay, then you can also guarantee that if you take like one of the theta t's which are generated later, that will also be very close to optimum. Okay. Okay. So so in order to prove, we define the following. So we define the expected loss, which is S of theta, which is with respect to the true probability distribution. So here there is no randomness. Okay. And we also have the optimal expected loss and the corresponding optimal parameters S star and theta star. Okay. So these are the actual ones. So there is no randomness. Okay. Now, the kind of guarantees that we are going to give is the following. We are going to say that, look, if we take expectation over this theta bar. Now, what does this expectation over theta bar means? You remember that this theta bar is also a random because each of these theta t's is random. Okay. So, if we take expectation over theta bar, okay, and then look at this expected loss. So there are two expectations here. One is an inner expectation over P, another is outer expectation over theta bar. Okay. If we look at that and compare that to the, so compare that to a star. Okay. Then what we can see is that, this is less than or equal to r square plus L square plus summation over t is equal to 1 to t eta t square by 2 summation over t is equal to 1 to t, okay, eta t. Okay. And now just so here R and L are constant. So so we will define what R and L are is. So R is basically your distance from the optimal solution of the initial solution. Okay. So in some sense you can think of this as sort of the size of the space. Okay. Diameter of the space. Okay. And L is like the maximum gradient of the loss. Okay, so this is sometimes also called the Lipschitz constant, okay, of the loss function. Okay, that is your gradient of the loss function, a bound on that. Okay, if these two are constant, that is the gradient is also not infinite, these two are finite basically. Okay, then you can make the following observation, that suppose your summation eta t square, okay, this is, or let us put it this way, that this is finite. So this is not infinite. Okay, but your summation eta t goes to infinity. Suppose as t tends to infinity. Okay, suppose these two conditions are holding. Okay, if these two conditions are holding, then what can you say? Okay, as capital T tends to infinity, okay, what you can say is that this particular so the numerator is finite. Okay, the numerator is finite, but the denominator is infinite. Okay, so this difference, upper bound on this difference, is a finite number divided by an infinite number, which is 0. Okay, so this upper bound goes to 0, which means that the expected loss of theta bar, when you take expectation over all the trajectories, okay, all the random trajectories, this is not much larger, or this is exactly equal to, as t tends to infinity, your actual loss. Okay, so this is the kind of guarantee that we will provide. Okay,